Hi, and welcome to core concept number 7. We're going to do elastic strings and springs, not elasticity, but elastic strings and springs. So in the last video, I had a little string and I told you it was inelastic in that it wouldn't stretch. And I also talked about a tension, a force of tension, and if that exceeds the tensile strength, that string would snap. So it just stayed in place, took the force, and when it exceeded the material property of that string, it snapped. This time, a little different. Those were not inelastic strings. We're going to talk about elastic strings and springs. Springs by nature are elastic. I'm only going to speak about some basic ideas here for you to understand this, a little bit of math, and then in the advanced series, I'll speak a little more about the same topic and how it relates to real dynamic equations, how the same thing relates to energy, things like that. Here, we'll keep it very simple. I'm assuming that for most high school syllabus, you should be good. Most of the elastic strings problems in dynamics are probably at the A level. There are some curricula where they teach them in high school physics, but most of them will kind of cover it'll be the basics that this video covers. To do that, first, I'm going to bring a couple exercise bands and then we'll start the conversation with that in hand. Okay, so here I have an elastic band. Okay. I've made myself a little cheat sheet kind of thing on this board, 15 centimeter markers. This elastic band works out to about 30 centimeters. Now, if I stretch this band, I'm holding the top and I stretch it out another 15, so there's an extra 15 centimeters. It snaps back, but so let's do that one more time. Snaps back. Now, observe if I get it here, but I'm still, I'm going to continue, and this is getting harder now. Oh, that was much louder. So the more I stretched it, the more it sort of pulled back, right? So that's the idea. With that in mind, we'll start talking about what we want to understand in elastic springs. Again, we're not talking elasticity, it's a material property. Some branches of physics, a lot of people in chemistry will talk about that, but we will talk about elastic springs. So what are we going to talk about here? We want to understand something called, we want to understand what exactly happened there as I stretched it. So the first thing you want to know is a term called tension. I use that term tensile strength for inelastic strings, which is basically that maximum limit that they can bear for the force that they can bear, right? Beyond that, they snap. Tension is what this material experiences as I'm stretching it. So when I let go, it was that tension, because that was a force. I'm pulling it down. So imagine Newton's third law. Something's pulling back at my finger or my fingers, right? My right hand, this hand. Something's pulling back, and that's the tension, right? And the more I pulled, the more that tension. Wow. So this is what is called tension. If I was working with a spring and I was compressing it, that spring would push up back at me, and that's called thrust. They're the same thing. I'm going to work with elastic strings. The spring is very similar. So I'll speak about the spring, but I'll work with the string. So tension. Now, one of the things I noticed, I hope I've demonstrated to you, is for a given elastic string, that tension here versus that really loud noise there, that tension is directly proportional to 1, the extension. What is that extension? That extension, so if this was 30 centimeters, each of these is 15 centimeters. So if I wrote 0.15, 0.3, 0.45, 0.6, and 0.75 here, that is an extension. The extension is this area that I've yanked this elastic string by. That is x, cursive x. That is the extension. And extension is x. Now that's very important. How much did this material get extended by? So if it was 30 centimeters and applying a force on it made it 45, its extension was x is 15 centimeters in this particular case. So tension is directly proportional to extension. I'm going to take this out for a second. Right? Now there is another thing, and let me bring another elastic band here just to illustrate what I mean. That's a much longer one. So maybe I'll do this. Okay. This one's, say, call it, well, it's going to almost double, right? But it is a different material, so it wouldn't be very fair doing this. So let me do this. Let me do this. I'll get this to 30 centimeters first, okay? And then I'm going to stretch. Wow, that's a tight one. Let me see if I can get it to 60. There is no way. Oh, yeah, I might be able to. So I've gotten it up to 60. Ooh, it's extremely, extremely painful. And that was not pleasant on my thumb. That took a lot of energy to get it there. However, so that was 30 to 60. Now I'm going to go down here and call it 90. Now let me just try this. So I gave it an extension of 30 centimeters. So here, maybe what I'll do is I'll do this for my red band. This is my X1. And I'm going to use this as a term called the length, L, but this is, right? But if I increase the length, so now I'm going to work with the spring to say, I want to double its initial size, and then I'm going to pull it. Oh, it's a lot easier. I can just get it to 90 centimeters very easily, 0.9 meters, very, very easily. A lot different from if I only had 30 and I wanted to get it to 60. That was stretching it. Ooh, that was hard, right? And you might be able to intuitively say, oh, yeah, there's much less of this material here. So it was harder. I mean, there's how much are you going to pull this by? Not a whole lot. But if you had 60, you had a lot more material and you could easily pull it right well away, right? You could say that, which means the longer the length, the initial length L, take that out, just call extension as X for now. The longer the initial length, the lesser the tension. So tension is inversely proportional to length. It's proportional to extension and it's inversely proportional to length. So if I wrote this, I'm going to use the term T, my equation would be T is maybe not equal to, I'll first write the proportionality of X divided by L. And if you think about it, intuitively, it makes sense, right? This represents the ratio or the amount by which an elastic string is extended or a spring is compressed, right? Because in a spring, this would be compression by how much it goes down, and tension will be replaced by thrust. But all of the others stay the same. So the greater the tension, the more you've extended it with respect to its original length. If L remained constant, higher the x, greater the t. Or if you knew x, but if the length became smaller, the original length was smaller for the same x, you'd have much higher tension. Now, these were two different materials. So clearly, this one, I had a struggle bringing it down. Well, not really. Let's see, it was still hard, but let me just get this here to 30. Yeah, that is very, very tough. And as you can see, this is thick. This is a really thick material. But let me get the other piece that I had. It's much thinner, and it was not, or it's not nearly as hard to bring it till here. It was just easy. This is my elastic band. That's, it's a lot easier to work with this. Something exists that is a property of the material, right? And that is what will help us change this proportionality into a equation. And what we're going to do is we'll replace that t equal to, and we need a constant of proportionality. In this case, we're going to use lambda, and we're going to define lambda as a property of the material, lambda, and we're going to call it the modulus of elasticity. And that's about where this term elasticity is going to come in for us, a property of a material. So we're not studying elasticity, we're studying mechanical properties of elastic strings and springs, right? Remember this, lambda. The same equation holds for a spring. The compression, total length, will give you the thrust, and the modulus of elasticity is still the modulus of elasticity. It's not the modulus of compressivity, or I don't think so. It's modulus of elasticity, right? This is an important equation that you will need to remember. You'll have exam questions where they give you the modulus of elasticity. They might give you this value x, this value L, or a combined value of L plus x in some form, and they might ask you to find t, but they'll often make it really creative. So what they might do, let me try and illustrate this with an example. So here's my key bunch, about 100 grams. But what I'm going to try and do is, this thing was 30 centimeters L. But what I might do here is just give you a view saying, okay, it was 30 centimeters on L, and this is not heavy enough. We might try and, forget it. Let's work with this. Let's assume that this is hanging out here, right? And we might ask you to say, what is either calculate the modulus of elasticity. Yeah, we could do that, of this elastic string if the weight of this key bunch was, let's say it's 200 grams. The weight of this key bunch is 200 grams, and let's say the original length is, let's say the original length 30 centimeters. Extended length is there, and it is in equilibrium. What might be the modulus of elasticity? That could be a question, right? So you effectively, that tension is that reactive force here. That's the reactive force that's acting against mass times gravity. So you'll have mass times, not gravity, acceleration due to gravity. That's one force acting downwards, right? And then tension's acting in the opposite direction, right? That's tension, and they're equal, and you don't know, and these are equal, and that's equal to lambda, which you don't know, times x here is 0.15. Maybe I should write x by L. And then if this was 200 grams, that's 2 kilograms, 0.2 kgs times 9.8, and then you would equate that to lambda, and if x was 0.15 and L was 0.3, you can see how the math would easily solve to give you a modulus of elasticity. Or they could just give you a modulus of elasticity, tell you if I had a 200-gram object on this length, what would be the extension? Or they might ask you, what's the total length, where you get the extension added to the initial length and find out the total length. They can play with it and ask you a few different types of problems here. But this is fundamentally what one needs to know when it comes to elastic strings and springs. It's not elastic strings is one and springs are the other, because springs are inherently elastic. So it's not elastic strings and elastic springs. It's elastic strings and springs. They should actually call it springs and elastic strings. That'd be much better. But this is typically what you will need for most high school curricula. The further mathematics, further mechanics portion at A levels will take this one level up and start applying this in dynamic movements. So if I had an inclined slope and a weight or a mass, it would, you'd start doing things like what would be the equilibrium force extending the spring by so and so, or extending the string by so and so. You'd get into those kind of problems, but we'll do that in the advanced concepts, because I think it's a lot better to study those, because then you begin to understand it in the concept of energy. I'll touch upon what happened with energy is. Remember, if I told you as I was carrying something up, I was doing work which was effectively increasing its potential energy, and as it fell down, its potential energy became kinetic energy. But if you really think about it, if I yank the spring all the way, this elastic string all the way here, and let go, just see what happened. It actually, flung that key bunch up. That in some way is really what's happening with energy. In some ways, if you think about it, by doing this, I'm increasing the potential energy in the elastic string, and when I let go, that potential energy is getting converted to kinetic energy, moving the spring upwards. So there's a lot more interesting mathematics that we can do. We'll keep all that for the advanced portion. I'll get to that video in a few days. So those of you who still want to continue the study of elastic strings and springs and elastic strings, can watch that hopefully in the next 3 to 4 days. That video should be up. But otherwise, for most other basic understandings of springs and elastic strings, I think this should be enough. This is called Hooke's law as well. Shouldn't forget to mention that. I think I will verify that. I think it's Hooke's law. I think that's what it's called. But remember the modulus of elasticity. There is a small point here that you need to keep in mind. Maybe I'll get another spring for that. Let's see. Actually, okay. Let me see if I can make it work with this. So here's an old elastic string that I had. It broke. So just as I explained, for an inelastic string, as you applied force, there was tension, and that lasts until the tensile strength of the string, inelastic string, is reached. For an elastic string, the force that I was applying and the resultant reactive tension kept increasing as the extension was increased up to a point where I had reached its limit of elasticity. It's a term you ought to know, limit of you can think of this as the breaking point. Just like how a normal string, if you gave it a very heavy load, would snap at some point. The limit of elasticity is where an elastic string would snap, or a spring would seize. There would be no further effect of compression on it. It may not break if compressed, it might just get compressed and just stay there. Hooke's law is only valid until you reach the limit of elasticity. Once it breaks, what's the, no more extension, no more tension, right? So think of that intuitively. Hope you get it. As I stretched that yellow elastic string, Hooke's law was applicable, but then the tension got to a point when I reached its limit of elasticity and the material snapped. Okay, that hopefully gives you a good view of what springs and elastic strings should be. Summarize: tension, that's the reactive force within the elastic string. In a spring that is compressed, it's called thrust. An elastic string that's stretched, the original length of the elastic string gets extended by an extension when it is stretched. The original length of a spring, L, when squeezed, gets compressed by a compression X. It reacts by providing a thrust in the case of a spring that is compressed. In the case of a string that is stretched, the reactive force is called tension. That's the ratio of, that's proportionality, and that's how we've equated those. That is, lambda is a material property called the modulus of elasticity. This relationship is called Hooke's law, and it's valid till the limit of elasticity is reached for that material. Hopefully this should give you a good idea, a fair idea to start attempting some problems there. And I'll see you in the next video of core concepts. And on this topic, I'll see you in the advanced concepts where we'll discuss how this applies in more detail. Until then, have fun.